Welcome to the lecture series on operations research. In today's lecture, let us understand the minimum spanning tree problem with constraints, how we can solve using taboo search. As a recap, let us revise the taboo search algorithm. Taboo search algorithm starts with the local search procedure. From the current solution, we get using the neighborhood structure, we get the next solutions. From the next solutions, we find out the best one by using a local search procedure. And we update the taboo list and we define the taboo move. The step 1 and 2 is allowed only if it is not a taboo move. And we repeat this particular process certain number of times until the stopping rule is met. Of course, we also need to determine some of the parameters like what is the length of the taboo list. So in the last video, we understood how we can solve the problem of traveling salesman problem using the taboo search algorithm. So we need to define answers to these particular 6 questions for the problem that we are solving, so that we can get a heuristic algorithm to solve the problem. So in this video, let us understand how we can solve the minimum spanning tree problem with constraints. What do you mean by minimum spanning tree problem with constraints? Already we know that minimum spanning tree is nothing but among the all possible, given a graph, construct a spanning tree consisting of n minus 1 number of edges so that there is no cycle. So, for example, if you consider A, B, E, C, D, there are 5 vertices and a certain number of edges are there. So, one possible tree may be AB, AC, AD and DE. These together, 4 edges forms a tree, a spanning tree. So among all such possibilities, the best one is nothing but total weights are less as much as possible. So that one is called as the minimum spanning tree. This particular problem we have discussed in module 2. We have used Prim's algorithm and Kruskal algorithm to find out the minimum spanning tree of a given graph. Now let us understand minimum spanning tree problem with the constraint. What do you mean by with constraint? Given a spanning tree, given a graph along with 2 constraints. The 2 constraints are link AD. The first constraint is link AD can be included only if link DE also included. So AD can be included, edge AD can be included only if DE can be included. This is the first constraint. The second constraint is at most one of the 3 links, that is AD, CD and AB. Among these 3 edges, only one can be added. At most one of the 3 links can be included in the minimum spanning tree. So we need a minimum spanning tree plus these 2 constraints needs to be met. So this is what the minimum spanning tree problem with constraints. So now the question is how we can design a taboo search algorithm to address this particular problem. To address with the taboo search problem, we need to answer those 6 questions, which is the skeleton of the taboo search. Of course, before getting into the 6 questions, how we can tackle that, let us understand what is the first solution, what is the initial solution we can start with. And also how we can define the problem. Now, minimum spanning tree means the objective function, basically it is the sum of all the edges. So we need to minimize the sum of all the edges of the spanning tree. That results the minimum spanning tree. Since 2 constraints are involved, how we can accommodate these 2 constraints as a part of the sum of the weights of the edges. So what we do is, to meet the constraints 1 and 2, we adopt the concept of penalties. Suppose the first constraint is violated. Suppose the first constraint is violated. The sum of the weight of the spanning tree is added with a penalty of 100. Similarly, if the constraint 2 is violated, penalty 100 will be added, or 200 will be added to the weight of the spanning tree. In detail, coming to the constraint 2, penalty of 100 is added if we select two edges, AD, CD, AB. If at all two edges are added into the spanning tree among these three, then the penalty of 100 is added. And if all three are part of the spanning tree, then penalty of 200 is added. So in general, the weight of the spanning tree is added with a penalty if the constraints are violated. Since we need to minimize the objective function, we need to find the minimum spanning tree. The objective function is nothing but the sum of the weights of the edges. So naturally, the minimum spanning tree, whenever we find, it will adjust such a way that these constraints will be satisfied and penalties will be nullified. So to start with the taboo search, we need one first feasible solution, trial solution, first solution or initial solution. So what we can do is, we can have the initial solution as is nothing but an optimal solution without considering the spanning tree, without considering the constraints. So if you just consider the problem of minimum spanning tree without constraints, the initial solution, the minimum spanning tree is nothing but AB, AC, CE and AD. These four edges forms the minimum spanning tree without constraints. Of course, the basic cost is 20 plus 10 plus 5 plus 15. That is come to be 50. But we define the penalties for the constraints, violating the constraints. So we can see that constraint 1, AD can be included only if DE can be included. So AD is included, but DE is not included. So first constraint is violated actually. So the penalty of 100 is added. Similarly, penalty of 100 if selected 2 of 3 edges or among AD, CD, AB. AD, CD, AB. We can see that among these 1, 2, 3 edges, we can see that two edges are part of the minimum spanning tree. So penalty of 100 is added because 2 out of 3 are present in the spanning tree. So I repeat, constraint 1 is violated here. AD is there but not DE is not there. So 100 penalty is added. Further, coming to the second constraint, we can see that among the 3 edges, AD, CD, AB, among the 3 edges, AD, CD and AB, among the 3 edges, 2 are present. That is why penalty 100 is added. So overall, the cost of the spanning tree is given as 50 plus 100 plus 100, which is equal to 250. So this is the initial solution we take. Now let us understand how we can define the answers to the 6 questions. That is the 6 parameters that we need. Let us understand one by one. First, we need to understand what is the local search procedure. Local search procedure is nothing but among the first solution. First is from the solution we get several other solutions. From the other solutions, how we select the best one. So that defines the local search procedure. So the one we choose here is, at each iteration, choose the best immediate neighbor of the current trial solution that is not ruled out by the taboo status. We need to get the several immediate neighboring solutions and take the best one which is not ruled out by the taboo status. Now the question is how to get the immediate neighbor. How to get the immediate neighbor means from one solution, one spanning tree, existing spanning tree, how to get the several other spanning trees. So that is defined by the neighborhood structure here. So it is defined as an immediate neighbor of the current trial solution is one that is reached by adding a single link and deleting one of the other links in the cycle that is formed by the addition of this link. The deleted link must come from the cycle in order to still have a spanning tree. So here the question is how to get the from one spanning tree, how to get the another spanning trees. So the basic logic involved here is we add one edge which is not a part of the spanning tree. For a spanning tree, if you add one edge, then it results a cycle. Then go for removing an edge that removes this cycle. So thus it results another spanning tree. So like this we need to do for all possibilities. I repeat, from the given spanning tree, which is a result of an iteration, we get the other spanning tree by adding one edge, which results a cycle, then removing one edge, which removes the cycle. So all the possibilities we need to explore and come out with all the other neighbors of the initial solution. So this is how the neighborhood structure is defined. So summing up step 1 and question number 1 and 2, get the immediate neighbor by using the neighborhood structure and choose the best one which does not rules out the taboo status. Coming to the question number 3, how we define the taboo moves. So taboo moves are made as list the links that should not be deleted. Whatever the moves that we should not delete, that we add to the taboo list. Per iteration, we add one edge, one link to the taboo list. Addition of the taboo move. At each iteration, after choosing the link to be added to the network, add that to the taboo list also. What we discussed in 1 and 2, whichever is the move is selected. For that, what is that? The link or edge that we are adding, that we need to add to the taboo list also. 5, step 5, question number 5 is what is the maximum size of the taboo list? In our case, here we list 2. The length of the taboo list is 2 so that it remembers previous 2 moves. So whenever a taboo move is added to a full list, whenever the list is full and we need to add another edge, delete the older one. So this is what we followed in the traveling salesman problem also. In a similar way, we follow this also. Coming to the last point, when we are supposed to stop. The stop after 3 consecutive iterations without an improvement of the best objective function value. The same thing we used in the last traveling salesman problem example also. The same thing we follow here. So this is how we define for the minimum spanning tree with constraints problem. So let us understand this with respect to one example. So let us consider the spanning tree. This is the spanning tree that is given to us. We start with the initial solution. It is nothing but this solution A, B, A, C, C, E and A, D. Now, of course, we have seen that the cost is 50 plus 100 plus 100. It is 250. 100 is because of the penalties. 50 is the actual cost of the tree. Now, let us go for addition and deletion, all the possibilities. Addition and deletion, all the possibilities. Now, let us take the edge BE. If you add BE to the existing spanning tree, there forms a cycle. There forms a cycle something like this. So if you add the edge BE, then remove this particular cycle, we can delete three edges, AB or AC or CE. So three deletions are possible. So we have three choices for us. By adding edge BE, we can delete CE or AC or AB. So these are the three resulting immediate neighbors of the original spanning tree. So this is what the three we got. Further, if you do this, we need to compute the cost also. The cost also, the cost is here it becomes 20 plus 30. Let us go for the first one. Add BE, delete CE. So add BE, delete CE. So 30 plus 20 plus 10 plus 15. So that results 75. Then due to the penalties, constraint 1 and constraint 2, the penalties we have 200. So altogether it is 275. Similarly, go for the next one. Add BE and delete AC. The cost of the spanning tree will be 70 and the penalty will be 200. So overall it is 270. Similarly, the third one, 60 plus 100, only one constraint is violated. So 60 plus 100, it is 160. So this is about adding B. Now we can go for adding CD. If you are adding CD, it results a cycle something like this. So to break the cycle, either we need to delete AC or AD. So AC or AD, that is what listed here. So these are the two possibilities. We'll get two spanning trees. Of course, their cost is also 160 and 365. So we can see that by deleting AC, we can see that the cost of the spanning tree is 65 and it violates both the constraints 1 and 2, adding 100 plus 200, so that the penalty is 300. So overall the cost is 365. The last one, going to delete DE. The cycle will be formed here, A, C, E, D. This cycle will be formed. To break the cycle, we can delete either AC or CE or AD. So these are the three possibilities we can have. So all these three possibilities, these are the possible cost: 185, 180, 75. Please note the taboo list as of now it is empty. So all the deletions are possible here. I mean, none of the moves are forbidden moves. So among the all 1, 2, 3, 4, 5, 6, 7, 8 possibilities, the best one is nothing but the last one, adding DE and deleting AD. So at the end of the iteration 1, we choose this particular move that results another spanning tree. So the new cost is 75, which is nothing but the local optimum. So since we are adding DE, so add DE to the network as well as add DE to the taboo list. Also delete AD from the spanning tree. So at the end of the iteration 1, we can see that the taboo list is having DE as an one edge, as well as the cost of the spanning tree is 75, and this is the new spanning tree. Coming to the iteration 2, the same steps are repeated. The steps here you can see, we can go for adding the edge AD. We can add the edge BE. We can add the edge CD. All three, there are deletion or some possibilities also listed in this particular table. Now let us discuss only few here. Adding AD and deleting DE. DE is already there in the taboo list. So this particular move is forbidden because we will go back to the previous move. That is the reason this is forbidden. Again, adding AD and deleting CE, the cost will be 185. Adding AD, deleting AC will give us 180. BEC will result 100. BAC will result 95. BAB will result 85. CDD, actually it is a taboo move, but one exception we are providing here. Why it is a taboo move? Taboo move because the edge we are deleting, the link we are deleting, it is in the taboo list. So there is a forbidden move actually, but still we are accepting it, because even though if you delete this one, we won't go back to our previous one, thinking that it may give the better that is what the better cost of the spanning tree. That is the reason we are allowing it, but of course it is not giving something better. Edges in the taboo list is used here so that it will not go to the earlier trial solution. Taboo moves are allowed if it results other than the previous solution. Okay, so edges in the taboo list is used so that it will not go to the earlier solution. So here it is forbidden because it will go to the previous solution. Here it is allowed because it won't go to the previous solution. This is what we call it as a aspiration condition. Even though D is there in the taboo list, it is allowed because the resultant spanning tree is not the one that we got in the iteration 1. It won't go back to previous solution. That is why we are allowing this, even though it is there in the taboo list. So we have around 7 solutions. We have 185, 180, 100, 95, 85, 160, 195. Altogether we have 7 solutions. Among that, the best one is 85. So add BE and delete AB from the network, from the spanning tree. Add BE and delete AB from the network, and also BE need to be added to the taboo list. The taboo list need to be updated with BE. So go to the iteration 3. Iteration 3, taboo list is D and B. The cost of the spanning tree is 85. The spanning tree is nothing but this one. Now again go for third iteration. So possibilities for the deletion is AB, AD and CD. AB, AD and CD. And deletion is of course possibilities are listed here. Among that, deletion of this BE edge will go to the earlier solution. That is why it is taboo. And this one, DE as well as this particular choice, it is allowed here just because it won't go back to the previous solution. It is the aspiration condition, hoping that we are getting some better solution. And that hope is clear here. We can see that we got some better solution. So 100, 95, 160, 95, 90, 70 and 105. The best one here it is 70. So that is because of adding CD and deleting D. So now iteration 3 at the end, the solution that we got is this one. So that is the beginning of the iteration 4. The cost is 70. Of course, we need to add CD to the network and delete DE from the network. And we need to add CD to the taboo list. So this is updated to the taboo list. CD is updated here, where the first one will be deleted. Stop. Iteration 4 and further iterations are not shown here. So this will continue as long as continuous 3 iterations, there won't be any improvement. The final optimal solution for us is nothing but the one that we got in got at the end of the iteration 3. Further, if you do the 3 iterations, we can observe that there is no improvement in the solution. So the optimal solution that we got by using this is 70 itself. So additional iterations also, if you do this particular for this particular taboo search, it won't give you better solutions, some inferior solutions only we will get. So this is what the final optimal minimum spanning tree with constraints for the given problem. So that is about another example of taboo search with minimum spanning tree with constraints. Thank you.